Welcome everyone to another session of discrete optimization talks. Just to go over the format really quickly, it's as usual, we're going to have about 25 minutes per speaker, and there's going to be time for 1 or 2 questions at the end, or in the middle, you can ask in the chat throughout the whole time. There will be much more time for questions in a one-on-one breakout rooms at 3 o'clock. So please stick around if you would like to ask more questions of the speakers in that format later. And also at that point, there'll be a little bit of a social time when you can hang out and talk to other attendees. And I would also really strongly encourage for everybody to join the Discord channel where you can ask questions asynchronously, participate in the community, start your own channels. Discrete optimization chats is what I'm calling it. And I think it'd be a really nice thing for everyone to participate in. So from here on, Elias, take it away.
Okay, thanks, Alex. Welcome everybody to this week's session of DOTS. I'm happy to introduce Professor Ricardo Fukasawa with us today. Ricardo is a professor in the Department of Combinatorics and Optimization at the University of Waterloo. Before that, he obtained his PhD in ACO from Georgia Tech and spent some time at IBM as Herman Goldstein postdoc fellow. His research interests are broadly in mixed integer programming, OR, stochastic programming, and he's going to tell us about some of his recent work in stochastic programming and scheduling today. So Ricardo, please go ahead.
So let me share my screen here.
Okay, looks good. Perfect, yes.
Okay. Yeah, so first of all, I'd like to thank the organizers, Elias and Alex. I think this is a great initiative to deal with this current times. And thanks for the invitation to speak. And thank you all for being here. So I'm going to be talking about this work that I've been doing with my PhD student, that's Kavita Menon, and a colleague in chemical engineering at Waterloo, Luis Ricardo Sandoval, where we're essentially dealing with a stochastic program on a scheduling application with endogenous uncertainties. So I've tried to give this talk with the least technical content as possible and trying to hopefully just give you the very high-level ideas of what we're doing, and hopefully I'll succeed on being clear despite the lack of formulas. By the way, feel free to interrupt me with questions. I mean, if you have any questions in the middle, I'm fine with responding them. So just send them via chat, and Alex or Elias can ask the question on our behalf. So here's the outline of what I'm going to talk about. I'm just first going to describe the overall scheduling problem, the deterministic one, and talk a bit about the type of uncertainty that we're considering. Then I'm going to talk about what we've done to address this scheduling problem with uncertainty. And then I'll conclude with some final thoughts on it. Okay, so here is the rough description of the problem. So the context is that we're doing a scheduling model for a company that does analytical services. So you can think of, I mean, maybe they receive some samples that need to go through some sequence of tasks that need to be essentially analyzed. They want to find out properties of them. So it can be soil samples, it can be rock samples, etc. I'm not going to mention the company's name because they don't want, they have confidentiality agreements, but this is the rough description. So I have a set of jobs that they want to receive or to process. They get on a daily basis, set I, and they have a set J of all the possible tasks that they have in this plant. Now, for each job, what is the description of each job? They receive some AI number of samples that need to go through a sequence of tasks. We call those sequence of tasks a path, right? And those, each one of those is a possible task inside J, right? So PI1 to PIQI, right? And they must go through this in order, right? And there is no preemption or anything. Once they start, they have to finish. And the units have to each one of them has to go on this order. But for example, if I have like 100 units here, they don't need to move together throughout the period, right? They can move 2 units, go first and do the tasks, and then another 5 go on, right? So they can be split up. So that's sort of the scheduling part of the problem. And then for each one of these tasks, they have some machines that are available, the total of RJ, each that has a constant processing time phi and a constant capacity CJ. And we want to do the scheduling over a time horizon H. That's typically 1 day, sometimes maybe a little bit more, but it's essentially the short-term scheduling where they want to have this. And then also another detail that needs to be considered is that the machines, they can mix things together, right? So you can think of this as really what you have is samples, so something like a test tube that are put inside the machines. So there's no real issue of contamination. So they can be all put together, tasks from different jobs inside a single machine. And the ultimate goal is that they want to schedule these units or these samples during the time horizon so as to maximize the number of samples that finish their final task. There's a lot more actually details that are in there and some things that I'm glossing over, so I'm lying a bit about some things. But I think that this gives you sort of just the main ideas of the things that need to be done. Okay, so this is just, again, a very simple example, but it helps illustrate what this process is. I have these 4 tasks, A, B, C, and D. Each one has their own capacity, and I have a red job and a green job. So the path of the red job is ABC, the path of the green job is ACD. So this is one potential schedule, right? It starts at 0. You put 30 in the task, in the machine of task A, and I'm assuming there is only one machine for each task. Then for task B, it has a processing time of 1 and a capacity of 5. So maybe it has to wait a bit for processing these guys on the red job. So it has to process 5 and then another 5 later on. Then for task C, it has a capacity of 20. And so they go 15, 5 of the red job and 15 of the green job here. And you can see that the green job waits a little bit from hour 2 to hour 3. Just so that it can be bunched together with these units of the red job, right? So this is, again, a very easy example to illustrate how the scheduling works and the main characteristics of it. And again, the very simple way that we did to model this, and again, simplifying some stuff, but the main idea is, again, to just do a time discretization. We have nodes for each task and time point. Right? And we have a final node that says we're finished, right? We're done. And then essentially the flow on this network, we have one network, for example, for the green job. And then the flow of this network is what would represent, for example, this green solution here, right? It starts at time 0, task A to 20. Then it's available at task C and it waits. The horizontal arcs are representing waiting. And then this diagonal arcs are representing that tasks are being processed. And so this essentially represents this green solution here on the right. And then you have another one of these for the red as well, right? So overall, that's the solution, but overall, that's, I mean, the representation of all possible decisions is essentially this flow network, right? And the solutions are going to be this multi-commodity flow problem here. Okay, so there is one commodity for every job. And then you have, again, just constraints on top of that sort of talk about capacity, right? So if you look at these 2 task A that start at time 0, these are sort of bunched together. They have to have a variable to control if a particular task is or a particular machine is turned on, and then it helps control the total capacity as well. Okay. I'm not going to go into the details of that, but hopefully everybody can get an idea of what's going on there. It's essentially this flow problem with capacities depending on machines. Okay, so what is the source of uncertainty that we're considering? That's sort of the deterministic model. Again, if you want me to review any of the deterministic model, you have questions about that, that may be a good time to ask. But if not, I'll just keep moving. So what is the uncertainty that we consider? First of all, let me go a bit into some uncertainty classification, and I'm following sort of the classification that Goel and Grossman have in this 2004 paper. So they classify uncertainty essentially as several types. One is sort of exogenous uncertainties. Those are uncertainties that essentially don't depend on any model decisions. Right, so anything that you do, it's not going to affect how the realization of the data is going to happen. And then there is endogenous uncertainties. Those essentially are ones that do depend on the model decision. So some variable is set maybe to 1, that's going to change something about the uncertainty. And they classify further the endogenous uncertainty in 2 types. One is what they call a type 1. Essentially something like this is that the parameter of uncertainty, they do depend on the model decisions, right? So for example, a very simple thing, you can think that if you invest in advertising, right, that's maybe your model decision. Do I invest in advertising or not? If I do, that can change the distribution of customers that are arriving next week, right? That maybe increases the average number of customers or something like that, right? So the parameters specifically, they depend on your model decisions. And the type 2 is where the time of uncertainty realization, they depend on the model decisions, right? So in some sense, you're not really controlling what happens or the parameters of the random variables that you're considering, but you don't really know when is it that you're going to learn what is the actual truth, right? What is the actual value of this random variable? So for instance, the classical example, and I think that's actually what Goel and Grossman studied in that paper, is if you're looking at exploring some oil field, right, and you want to find out maybe the quality of the oil field or the amount of oil that is there, that they consider that as a random variable. And you'll only find that out once you actually decide to drill into it, right? So the time of the uncertainty realization is what varies based on the model that you do. Okay, and so first of all, most research has been mostly on exogenous uncertainty, where you have a very clear point where uncertainty gets realized, and then the uncertainty is just a given random variable that you have no control over or no influence over. What we're going to be doing is focusing on type 2 uncertainty, because that's the natural occurring uncertainty for our application. What's typically done in that context is that you add binary variables to indicate when uncertainty occurs. So you have some variable saying, okay, when is it that I'm going to decide to explore an oil field, right? And then you have a binary variable that says that, and then you use those additional binary variables to enforce non-anticipativity, okay? And then a lot of the research is just to mitigate the negative computational effects of adding all these huge number of extra binary variables. Typically, you need big M type constraints, and so you need to make sure that all of those things get to a computationally acceptable level of execution. Okay, what I want to present is our approach to deal with this uncertainty for our problem. Where we're dealing with type 2 uncertainty, and we don't need to add any extra binary variables, okay? So that was our big thing that we were able to do with this work. Okay, so what is it that we do? What is this real source of uncertainty for our problem? And so for the application that we're doing, what goes wrong is the following. The success of a task, it can depend of some factors, right? So these are samples that are trying to be analyzed. They do depend on some human accuracy. People have to prepare the samples before they put in the machine. There's calibration on the machine. There's sometimes quality of material, and there's other miscellaneous factors. But essentially, a task can go wrong. So as a result, part of the units may need to go back to a previous point in the path, right? That's what we call a recycle, right? So maybe you're at task A, B, C, D. You've just finished task D and you realize that, well, maybe you actually need to go back to task D again because something went wrong, okay? And whenever that happens, you call that task an imperfect task. So that's the type of uncertainty that we're going to be doing. So this is what we're going to assume, right? We had a flow problem, essentially this type of multi-commodity flow. Now we're going to assume that there is now a recycle rate, rho of S. So there's a set of scenarios that is given. So I is the index of a job. So there is a recycle for a scenario for a given job. That's essentially the fraction that moves from task K to task N, okay? So you can think of this as, in the deterministic case, it's just one for the previous task to the next task, right? But now I'm allowed to go from a forward task to a backward one. We're going to assume that these guys are between a lower and upper bound, the common lower and upper bound for every scenario. We're going to assume that there is no loss. So essentially, every sample that goes in needs to either go forward or move back, right? So that's what we're saying here, that the sum is 1. We're assuming that there is at most one imperfect task per job. So only one task really where you can, when you can have these recycles. And that this imperfect task goes back to exactly one previous task. Okay. And finally, we assume that these rows remain constant. What does that mean is that every time that a machine is executed, I'm going to have exactly the same rate for every scenario. Most of these are actually reasonable for the application. Assumption 1 through 4. This is really what happens for them. They don't have any loss of samples. They have a lower and upper bound. That's a very mild assumption in any case. But typically what happens is that they actually go forward all the way to pretty much the last task or the next to last. And there is where they have a check. And then when that check goes wrong, they know exactly to the point where they essentially need to restart it. So the assumption 3 and 4 really is the way they do these operations. Assumption 5 is not really reasonable, but I'm going to comment on that more towards the end. Okay.
Ricardo, quick question
yes.
from me. So when they do the check and realize they need to go back to a task, say they realize at D they need to go back to B, do they then go back to B and then C and then D?
Yes, they have to go through the same path all over again.
Okay,
yes.
Okay,
yeah.
Got it. Thanks.
So by the way, there's also one extra thing. I'm just assuming there is a constant fraction of the units that move back, so they may lead to fractional flows. And that's also not too good, but for our purposes, the number of units that are received is from like hundreds. So if there's like maybe one off, we think that that's not too bad of an assumption to have. Okay. So here's an example, right? So here's again what we'd see as sort of the deterministic flow on the green job, right? Is what I showed before. So here is maybe one thing that happens is that, well, you know, these 10 units that were here, right? That were going up here, they actually, half of them need to go forward, right? So the row of S for the green job, for D to the next one, which is being done, is half. So half of them go forward and half of them go back to task A, right? And from that point on, yes, they need to go through the same sequence again, A, C, and D. And that's pretty much what their operation is looking like. Okay, so how did we deal with this problem? So we tried to do a two-stage model for this, right? Where the first stage decisions is essentially, well, the machine schedule, when each machine will be operated, and also a plan on how the samples will be scheduled in those machines, assuming a default rate, rho 0, okay? That essentially leads to what it's called a first stage flow. The fact that machine schedules are first stage decisions, essentially they cannot be changed based on each scenario, is also something that we're okay with, because you can think of, again, there are people that need to operate these things every day. And so they like to know exactly, I mean, what are they going to be doing throughout the day? So they don't want to just say, oh, this happened, now my whole schedule changed depending on particular scenario. So we'll give them a fixed machine schedule, and just what changes is maybe the which samples are going in the machine, right? And that's a lot easier to deal with as change. And then once that's done, once this first stage plan is done, our second stage decisions is saying, well, given the particularization that happened, it probably is going to be different than this default rate that we assumed. What are the changes in the sample schedule that are needed, right? And that's what I'm going to call correction, and I'm going to mark that as a red in the following example. And so we're going to have a second stage flow, which is essentially the first stage flow plus that correction. So here's again the example, right? So I'm assuming this first stage flow, assuming that everything goes forward, right? The row 0 that we're assuming is that there is no imperfection here actually. Task D, everything that starts here gets finished. And so this is 100% goes forward. There's no imperfection really, right? But then if something happens, let's say the actual recycle rate is half, so half of it goes back and half of it goes forward, then what's going to happen? I need to correct that. So these 10 units, 5 actually didn't go through, so there is a correction of -5 here. So these -5 go here, and then 5 goes there, right? And these 5 that went back, then they can continue flowing that way, right? So these corrections, they can actually be negative, right? Because you may need to undo something that the first stage decisions took into account, right? But then at the end of the day, the second stage flow is essentially what was the first stage plus that correction. So that's what I'm showing in purple, right? So it's still a flow for a particular scenario, right? That's the second stage flow. Okay, so hopefully that gives you, again, the general idea of the type of two-stage stochastic program that we're considering without actually ever presenting the model. But again, this is where I'd like to point out, right, is that we actually only start seeing what is the actual recycle rate once this flow here happens, right? So that's why it's a type 2 uncertainty, because I don't really know when this machine is going to be turned on. That's the model that's going to decide that, right? So that the time of uncertainty realization is going to depend on my decision variables, and that's why it's a type 2 uncertainty. Okay, so the main thing that we needed to figure out is what is this choice of the default rate row 0. Different choices will obviously lead to different solutions. And so we try to think, okay, what is the good choice, right? What are choices that lead to good formulations? So let me just remind you of the first two assumptions that we have is that these, again, there is an upper and a lower bound for these recycle rates for every scenario, and that they add up to 1 for a particular scenario. And then the first stage decisions, I mean, there are several possible choices, right, of these row 0. But the one that we found that will work is that we'll only take the decisions knowing for sure what will happen, right? So what we do is the following. We assume that everything that goes back is happening at the lowest possible rate, right? So for sure, that's the lowest amount that needs to be recycled. It's this lower bound here, right, for any backward edge. And the, and the highest amount that we can assume for certain that's going forward is 1 minus the largest backward rate, right? This U here. And I'll make these numbers a little bit more clear in the example. But that particularly implies that the default rates row 0, they're not actually summing up to 1, which also implies that the first stage decisions, they're actually no longer flows. But that's fine. It's just essentially a plan. And we consider that's what we consider these flows is we consider these flows as a plan up to the point where you have an uncertainty realized. And when that uncertainty gets realized, then you start looking at just the second stage of decision variables, and those will always be flows, okay? So let me put this in a little bit more concrete terms, right? So for example, this is what the first stage decisions would look like, right? So this is the first stage flow, assuming that this recycle rate going back from task D to task A is between 0.1 and 0.5, right? So you have the natural flow here of 20 units and then 5 units here, 15 here. That's fine because up to that point, no uncertainty gets realized. But then how many of these 15 go forward? 5 are waiting here, so that's fine. So I was going to send 10 throughout the task here. All I can assume is that, well, half of them is guaranteed to go through because half of them is at most what's coming back, right? This recycle rate is at most half. So at least half will go through, and that's what we're assuming. This is the first stage sort of pseudo flow. It's not really a flow, right? So 5 of them move forward, and the same here, right? We had another 10 going in, so 5 of them actually end up moving forward. And then how many are we guaranteed that are going back? It's at least 10% of these 10 that are going forward, so it's 1 here, right? So we have 15 here. It's supposed to be 5 and 10, but it's actually 5 going forward and 1 going back. So that's why I'm saying this is not a flow anymore. But hopefully that becomes a little bit more clear what the choice of parameters is that we had. Okay, and that our result is that essentially if you do these, under these conditions and under the original assumptions that we have, we're able to essentially enforce non-anticipativity without any auxiliary binary variables. What do we mean by non-anticipativity? If we look at any of the second stage decision variables, they're going to be the same all the way up to this point, at least where the first uncertainty gets realized, right? And that's true for every job, okay? So that's pretty much the result that we had, and this is a part of ongoing work. We've done some preliminary experiments on that. I'm not going to go over the proof for this result, but it's essentially considering flow conservation and the sign of the second stage decision variables and the correction variables. That's what allows us to show that all the second stage flows are constant. We just do some preliminary experiments just with the extensive formulation, right? So no decomposition approaches at all. 50 scenarios, a low number of jobs. We do evaluation using the 1,000 out of sample scenarios. It's essentially roughly 10% better than deterministic approach. There's a lot more thing to be done. I mean, first of all, these sizes are not realistic. But we think that, I mean, we didn't even implement the approach with binary variables because we didn't see much of a point there. I think it was pretty clear that this was going to be a winner compared to that. But I mean, we need to do sort of a much better job computationally than this, right? So this is just part of ongoing work. So last, I think maybe I still have 1 minute or so. Yeah, so I just wanted to comment on this assumption 5 that I said it's not really a reasonable assumption, is that every time you run a machine, you're going to get exactly the same recycle rate. That's really not true. So it depends on every time you run, it's going to be different. But that's what we needed to do to make the proof work. It's reasonable if I mean, the machine actually only gets executed once, then it's true because I mean, it's only one time. And that can happen because for some machines where the processing time is relatively big. But it doesn't always happen. So what we want to do eventually is that we want to divide the time horizon into smaller time horizons. And then essentially every single one of these time horizons is going to become one stage of the uncertainty that leads to essentially a multi-stage problem. And we have some work on that. And I think that's, I mean, we can pretty much solve that multi-stage problem with the same type of assumptions. Okay. And so this is, again, just the general conclusion of the talk. That's what we did. We did this practical scheduling problem under this type 2 uncertainty without any extra binary variables. I think, again, some of these assumptions are okay for our problem. But I think I mean, probably some of these ideas could be used also in different scheduling problems where you have these schedulings based on this flow formulation on time discretized networks. I think that may be possible to do as well in similar type of problems. And again, as I said, there's future work to be done in terms of implementation and the multi-stage. And that's all I wanted to say. Thank you.
Okay, thanks, Ricardo, for a nice talk. In the interest of time, if you have a question, please meet us at 3 p.m. after Austin's talk, and you can ask Ricardo all kinds of questions. Alex?
Thank you. Thanks, Ricardo.